This video will go over the multiple choice questions posted in our Unit 2 review. So read question 1, see if you can answer it, and you can check on the next slide. We got computer output for a result of a linear regression analysis for predicting the concentration of zinc in parts per million from the concentration of lead in parts per million found in fish from a certain river. Remember, this is going to be your slope, and this will be your y-intercept. So the question says, which of the following statements is a correct interpretation of the 19.0 value in the output? So your x value is going to be your lead, and your y value is going to be your concentration of zinc, because that's what we're predicting. And let's see if you can answer the question correctly. Okay, the correct answer should be B. Remember, for slope, we have a interpretation as x increases by 1 unit, the predicted y variable increases or decreases also by whatever the slope value is. So in this case here, on average, there is a predicted increase of 19.0 parts per million in concentration of zinc, and that's your y value. For every increase, for every 1 unit of 1 parts per million in concentration of lead found in fish. So this is the correct interpretation based off of what we know about slope. Question 2. There's a linear relationship between the number of chirps made by the striped ground cricket and the air temperature. A least squares fit of some data collected by a biologist gives the model y hat equals 25.2 plus 3.3x, where x is the number of chirps per minute and y hat is the estimated temperature in degrees Fahrenheit. What's the predicted increase in temperature that corresponds to an increase of 5 chirps per minute? All right, see if you can figure this one out. This one's kind of tricky. All right, now what you want to be careful on this one is you don't want to just plug in 5. Okay, the problem is if you just plug in 5, you have 25.2 plus 3.3 times 5. But the problem is that we're not predicting 5. We're predicting from 9 to 25. Okay, so if you plugged in that number, you're going to get the predicted number of the predicted temperature in degrees Fahrenheit from 5 chirps, not the predicted increase in temperature. In order to do that, what I want to do is I want to think about, all right, let's find a reasonable value to plug in. Let's say maybe 10. If I plug in 10, I'm going to get 58.2. So if I plug in 10 chirps, I want to get 58.2 degrees Fahrenheit, right? Now, if I increase that 5 chirps per minute, I'm actually going up to 15. And I just made up 10, to kind of drive the point home. So then I'd plug in 15, and you'd see, okay, well, if I plug in 15, I'm going to get 74.7 degrees Fahrenheit. So the question here is, what is the predicted increase in temperature? Well, that increase, you're going to subtract that 74.7 minus the 58.2, and you'd get 16.5. Now, if you just ignore this part, right, and if you do 3.3, the slope, times that 5, you would actually end up getting that, because then you're not incorporating the y-intercept or your starting value. You're just saying how much, as this goes up by 5, each one goes up by 3.3. So 3.3 times 5 is going to be 16.5. So you can do it either this way or just plug in the 5 into the 3.3 and ignore that number, and you'll get your value. Tricky question. Number 3. Exercise psychologists are investigating the relationship between lean body mass in kilograms and the resting metabolic rate in calories per day in sedentary males. Based on the computer output above, which of the following is the best interpretation of the value of the slope of the least squares regression line? Once again, we're looking for this number. That's your slope. So we can automatically kind of eliminate anything that's not those. And now we're down to like one of these two. Okay? So read through those interpretations. For each additional kilogram of lean body mass, the resting metabolic rate increases on average of 22.563 calories per day. or for each additional calorie per day for the resting metabolic rate, the lean body mass increases on average by 22.563 kilograms. And the correct answer is A. Remember, for slope, for every x unit increase, the predicted y variable increases or decreases by whatever the slope is. So it's the y variable here being the predicted resting metabolic rate. That's how much it's going up by as the kilograms increases by 1 unit. So for each additional kilogram, the resting metabolic rate increases by 22.563 calories on average, predicted. All right, number 4. This is probably the trickiest one on here. Consider the n pairs of numbers x1, y1, x2, y2, and so forth. The mean and standard deviation of the x values are x bar equals 5, s of x equals 4, respectively, and then they give you the same thing for the y's. Y bar is 10, s of y is 10, respectively. Of the following, which could be the least squares regression line? Now, we don't have the r value. We don't have the slope or the correlation coefficient. So in this case here, this is what we know. Okay, we know that r times s of y over s of x, we know that is going to be equal to the slope, right? That's all I got to work with here. All right, I can't figure out what my 5 and y are, but what I can do is this. All right, I know that this right here and that have to go through the equation. So what I'm looking for is, if I do 10 equals, well, forget that for a minute. If I start with letter A, if I say negative 5.0 plus 3.0 times, what's my x bar, 5? I know that has to give me, if this is even worth looking at, that has to give me my y bar, right? So that should be equal to 10 if that's one of my possible equations. So if you do a little math on there, that's 15 minus 5, and that's going to be 10, right? But are we just lucky? Are all of them going to be like that? Or maybe we can narrow it down to a couple. If I plug in 10 here, or 5 here, I'm going to get 15, not 10. So that's no good. If I plug in 5 here, I'm going to get, what's it, 2.5 times 5 plus 5? That's going to be 17.5, way too high. If I plug in 5 here, let's see, 5 times 3 is 15. That's going to give me 10. All right, so that's a possibility. And if I plug in 5 here, let's see, 5 times 0.4. Let's see, 4 times 5 is 20, so 0.2. Or no, it's 2. And so 10 plus 2 is going to be 12. So now I've narrowed it down to 2 possible choices, right? I got negative 5.0 plus 3.0x and 8.5 plus 0.3x. And I feel like I'm at a crossroads, right? But one of those is a possible equation while the other one is impossible. Can you figure it out based off of this information? Well, turns out it's going to be answer choice D. Now here's why. Now if I know that s of y is 10 and s of x is 4, and I plug those into here, even though I don't know r, I know that r has to be between negative 1 and 1. And since this is a positive slope, well, then it's going to be somewhere between 0 and 1, right? R cannot be greater than 1. So if I try to plug in, well, you know, if I did 2.5, because 10 divided by 4 is 2.5, and if I did, 3, let's look at my b value here. If I divided 3 by 2.5, that would give me an R value of 1.2. Impossible. That is not possible. So the only one that would actually make sense in this problem is answer choice D. All right, if I did 0.3 equals 2.5 times R, and I divided 0.3 by 2.5, sorry for my sloppy handwriting, I end up getting 0.12, which is, you know, it's not a very good value of R, but it's definitely a possible value of R. See what I'm saying? So D is going to be my only possible choice in this scenario. All right, number 5, the correlation coefficient. What does that measure? Whether there's a relationship between two variables, the strength of the relationship between the two quantitative variables, whether or not a scatter plot shows an interesting pattern, whether a cause and effect relation exists, or the strength of the linear relationship. Well, that's a textbook definition right here. Correlation is the strength of a linear association, a linear relationship. That is what R is. So it's going to be answer choice E. 6, which of the following is true for the correlation of R? It is a resistant measure of association. No, the R value can change based off of the influential points or the outliers that you put on the graph. So it is not resistant. It is between -1 and 1. That is true. If R is the correlation between X and Y, then -R is the correlations between Y and X. That is false. R will not change if you switch to variables. Whenever all the data lie on a perfectly straight line, the correlation will always be equal to +1. No, it could be -1. Those 2 points have a correlation of -1. So that's not true. And it can't be this one. So it's going to be B. All right, number 7. Study gathers data on the outside temperature during winter in degrees Fahrenheit and the amount of natural gas a household consumes in cubic feet per day. Call the temperature X and the gas consumption Y. The house is heated with gas, so X helps explain Y. The least squares regression line for predicting gas is Y hat equals 1344 minus 19X. When the temperature goes up 1 degree, what happens to the gas usage predicted by the regression line? Well, the slope is -19. So as X increases by 1, the Y value, what does it do? It goes down. It decreases. So for X unit increase of 1, the predicted Y variable decreases in this case because it's a negative slope. Number 8, a least squares regression line is created for predicting stopping distance Y in feet from temperature X in degree Fahrenheit. If stopping distance was expressed in yards instead of feet, how would the correlation R between temperatures and stopping distance change? Well, remember, R doesn't have a unit. So trying to convert the units on your variables isn't going to change that strength of the relationship. So it's going to be C. Units do not affect R at all. Switching X and Y doesn't affect R. It affects the slope, but it doesn't affect R. 9, the percent of variation in the values of Y that is explained by the least squares regression on Y is, that's R squared. That is your coefficient of determination. About this percent of the variation in Y is explained by X. But since we don't have the words coefficient of determination, we'd say the square of the correlation coefficient, R squared. Number 10, which of the following statements about influential points are true? Influential points have large residuals. Not necessarily. You can have a graph that looks like this. A bunch of points over here. And then this point over here. This doesn't have a large residual, but it's definitely influencing the line. So that is not true. Influential removal of an influential point sharply affects the regression line. Let's see. Usually it does, right? If I take that away, then it's probably going to be a little bit less of a relationship in this case, or if it's down here, it might increase or decrease the slope, so that's true. Outliers are influential points. Let's see if I got some points here. Throw an outlier in there. Yeah, it's going to bring that down. Yep. So it's going to be 2 and 3, I think. Outliers are considered influential points, but if you take an influential point out, it's gonna affect that regression line. But they don't have to have large residuals. You understand? All right, number 11. The sum of the residuals which of the following statements concerning residuals is true? The sum of the residuals for a good regression line is approximately 0. Let's see. Usually that's the case, right? You got, they're not the squared residuals, the sum though. You got positive, negative, positive, negative. Yeah, those are usually typically going to add up to around 0, give or take a couple decimal points. So that's true. The plot of the residuals is useful for determining whether a linear model is appropriate for the data. That's also true. We want to look for a random scatter. And then part C, the value of the residual is the observed value of the response minus the value of the response that one would predict from the least squares regression line. So y minus y hat, in other words, that is also true, which means that all of these are true. So we're looking for a random scatter for B. All right, number 12. Using least squares regression, I determined that the logarithm base 10 of the population of a country is approximately described by the equation log of population is negative 13.5 plus 0.01 times the year. Based on the equation, the population of the country in the year 2000 should be about, well, you plug in 2000 and let's see what we get. So negative 13.5 plus 0.01 times 2000. What do you get for that? All right, I got 6.5, which that is the log of that number, right? So to undo a log, you take the base, raise it to that power. And 10 to the 6.5 power is which one of those numbers, guys? That's right, it's going to be 3.167 million. So you can see that make sure that you do the 10 to that power, because it doesn't make sense, right? Population is not going to be 6.5 people. That doesn't make any sense. So read through it, try to make some decisions based off the context too. Number 13, which of the following would provide evidence that a power model appropriately describes the relationship between a response y and an explanatory variable x? So a scatter plot of y versus x looks approximately linear. That's a linear model, not power. Scatter plot of log y versus x looks linear. Actually, that's log. Anytime you're just logging the y, that's exponential. Scatter plot of y versus log of x. We don't do that. We don't ever do that one. Scatter plot of log y versus log x is approximately linear. That's your power model. Power model log x and log y, not just log y. And our last one. Students in Miss Lohman's class dropped a kickball beneath a motion detector. The detector recorded the height of the ball in feet as it bounced up and down several times. Here is the computer output from a linear regression analysis of the transformed data, Ln, height versus bounce number. Predict the highest point the ball reaches on its 7th bounce. Well, we have our equation here, transformed data of Ln height. So we're going to say Ln height predicted equals 0.45374. That's a negative, so I'll say minus 0.11716. And then we want to know on the 7th bounce, so x is going to be 7. So let's pull up the calculator and see what we got. All right, let's plug that in. 0.45374. Let's put all the decimals in. Minus 0.11716 times 7. And you get negative 0.36638, which is ridiculous. That doesn't make any sense. But Ln, to undo Ln, we're going to do second Ln, right? And we do e to that power. And you end up getting a value that's one of the ones down there. So 0.6932 is the predicted height after 7 bounces. So you can see that 0.69 is right over there. And there's your work. All right, guys, if you needed any extra review, you're going to want to pry open your textbook, go to page 238 through 245. You don't have to, it's not required, but it'll just kind of help you get reviewed for the unit. And that's going to be here. If you're going on Sapling, you can find the Unit 3 review on page, let's see, click on that for a moment. Guess that starts right there. Do any or all, they have little explanations if you play on those on the online book. Then there are the review exercises. There is also a practice test with some multiple choice questions and some free response. And if you're interested in checking the answers, here are the free responses. There is a back matter here. Let's see here. There's a solution section. And if you do click on the solutions, you should see descriptions for all the free response. We're in chapter 3. I think we're almost there. Oh, there's chapter 2. Here we go. So chapter 3 is, you know, it does have selected answers in the back of the book. But if you're looking for the actual review exercises, it starts right here on S17. And it gives you their textbook answers for the review sections. Then it also has just letter choice answers for the practice test that's in there, as well as answers for the free responses on there. You're welcome to do those if you want some extra practice, and let me know if you have any questions. Bye.